Welcome viewers. In this video we are going to do design of lifting plates using robot structural analysis. This video is having a two part. One is the first part is the design of element. The second part is the design of connections that we are going to do next after this. So what is lifting plates? You can see on the picture there are two picture in the left hand side top. So this kind of arrangement you might have seen in many of the container or many of the prefabricated engineering building or pre-engineered structures. You may see this to lift those during erections or for container to shipping, to move this container to the shipping ship. There are some lifting arrangement we need to provide on the container or any of the structure part. So this kind of small lifting hook we need to provide whenever the structure or container is subject to a lifting requirement. So for that we need to design this, we need to finalize the thickness, which how much thickness is required to hold the container capacity or all those things we need to calculate. So in this two video we will be doing this design of lifting plate along with that bolt connection design. So in the first part what we are going to do is we are going to model this kind of similar kind of plate in the robot structural analysis. We are going to apply the assumed or tentative load values, maybe 5 ton lifting capacity. Then we are going to do design and analysis. In that, after that analysis, we are going to check the stress value, which should be less than the yield stress of the grade of steel plate which we had assumed. So with that, this part 1 will explain how to design the element. So let me go in detail about this design of element in robot structural analysis. Before going to do model, load application and analysis in robot structural analysis, we need to prepare a Excel calculation sheet where it is a ready reference for the model and load calculation to robot structural analysis. So that Excel calculation should consist of input dimensions and loads, and maybe design of connection bolt we can develop in this Excel sheet, so that all these parameters we can directly feed if it is required in the robot structural analysis, and we can also extract the load, the forces from the robot structural analysis and apply in the design of connection bolt, which we are going to look into that part 2 of this series of video. So this Excel sheet you can see on the screen, which is having input. Input means this should include the structural steel grade, which is covering the ultimate tensile strength, yield strength according to the grade of steel which we had selected here. So there are other grade such as S235, S275 and S450 also available as per European standard. So here we can consider only the S355. So accordingly this grade of steel, it will, the ultimate and yield strength will vary. This we can refer table 7 in European standard EN 10025 part 2. Anyway, we are going to consider the thickness of plate greater than 16 mm. So we need to consider this column for yield strength and this column for ultimate tensile stress. So next, the dimensions which we are going to assume for the demonstration purpose is the purport plate, the bottom plate or fixing plate to the container or pre-engineered building or pre-engineered structures is having a dimension of 300 by 200, 300 in horizontal direction and 200 in vertical directions, having a 4 bolt to fix on the structural part is at a distance of 200 mm in horizontal and 100 mm in vertical. So this plate thickness, the major plate thickness we can assume as 20 mm, both the purple color and the red color, which is extended from the base plate or the purple plate to hold the rope for a lifting rope. Lifting rope can be inserted on this 50 dia hole which we are going to make on the red color plate, so that the stress analysis on the hole also we need to do in the robot structural analysis. And the total length of the lifting arrangement from the fixing point, that is the left hand side of the purple plate, to the edge of the red color plate is 250 mm, which we are assuming this. In that we know that plate thickness is 20 mm, the purple plate, and the red color plate also 20 mm. So from that, the edge distance we are making for the shackle rope is 80 mm. So from the edge of the red color plate, it is 80 mm to the center of the hole, so that the center of the hole to the purple right hand side edge, it is 150 mm. So this is what the model we need to prepare in robot structural analysis for our demonstration purpose. We are not going to consider any arc here which is showing in the title sheet because of the time consideration. So now let we look into that loads parameters, how the load we are going to consider. So the load lifting shackle capacity we are considering as a 5 ton. 5 ton is nothing but in the right hand side you can see the picture, the P value which is having in the direction of inclination direction with respect to the plate alignment. So this P is a 5 ton, which here the center of this equilateral triangle rope will have the lifting point at this edge apex, which will have both side 5 ton. So here we can consider a 5 ton as a lifting capacity per plate. So this 5 ton is a inclination of equilateral triangle maybe 60 degree. So with respect to this, there is a 60-degree inclination. So we are considering the 60-degree as an inclination. So this 5 ton we are converting into kilonewton, just multiplying with 9.81. And the vertical force we can arrive by applying the sine theta trigonometry equation. So that is 43.31 kilonewton is vertical, and for horizontal force it is a cos theta, it is 25 kilonewton. So these are the model dimensions and the loads which we are going to apply on the robot structural analysis. Let me look into the robot structural model. So this is a robot structural main window. In that click new. Select the fourth icon from the left in the top, shell design. Then we need to create a grid line. For that select that right hand side top axis definition. So here in the picture you can see the total length of the purple line is 300 mm. So here what we have to do is we are going to take 0 as a edge of the plate, top edge of the plate, the left hand side X we are going to consider as edge of the plate in the bottom. So that is 0. From the edge to the center of the bolt, left hand side bolt we are consider 50 mm. So because on the screen in the picture you can see in the right hand side bottom 300 is a total width of the purple plate or fixed plate. In that center to center distance of bolt is 200 mm. So calculating the center to distance from the edge of the plate, it is 300 minus 200 divided by the whole things divided by 2, 50 mm. So 50 mm is the edge distance for the bolt. So here we are entering here 0.05 as a second grid line. And the third grid line we can consider the center line of the purple plate. So it is 0.15. Fourth one, again it is a right hand side anchor bolt or a fixing bolt. So that again it is a 300 minus 200, the whole thing divided by 2 is a 50 mm. So 50 mm should be deducted from the 300 mm so that we can find out the distance from the edge left edge of the plate. So it is 0.25, only the 50 mm we need to deduct. And finally the right edge of the plate is 0.3, which is the total width of the plate. We can apply here, click apply in the bottom, and next we need to define the y axis. So for y axis, again first axis we can consider 0. In the second axis you can see in the side view, that is a right side picture in the bottom. So you can, the purple plate is the first one having a 20 mm thickness. After that there is a red color plate which is a lifting plate for rope fixing. So that also having a green color stiffener plate on the both the side. So in the elevation view we can see there is a green color plate in both the side of the red color plate. So that we can call it as a stiffener plate for this red color plate. So that the plate length is just modified as a 80 mm instead of 230 mm in our just few minutes back video on our few minutes back. So that 80 mm we are going to consider. So this 80 mm plus this 20 mm is totally 100 mm. So from the left side the y distance is totally 100 mm. So we need to consider this 0.1 meter, that is 100 mm for the stiffener plate axis. And the next one is the center of the hole, the 50 mm hole you can see on the right hand side view, the orange color. So that whole center line we need to mark it in with another axis. So we know that 100 mm is the plate. You can see in the purple plate thickness in the top for side view it is a 20 mm. 20 plus 150 mm, so totally it is 170. So that will be the grid line for whole center. So 0.17 we are adding another grid line. And finally the edge of the red color plate, which is total length is 250. So that we are going to enter here and click apply. And next we need to define the z axis. Z axis, the first axis, again it is a 0. And here we are going to mark the grid line from the bottom of the purple plate. You can see on the elevation. So the first is 0. We had fixed the first bottom edge of the purple plate is 0. Then we need to mark this 150 mm. In the right hand side you can see that the dimension is mentioned for red color plate is 150, which is vertical distance. So that 150 we need to consider from the bottom of the edge it is 25 mm. For example, the 200 is the total depth of the plate, purple plate. That minus 150 divided by 2 will be the 25. So we need to consider here 0.25. The next one is the bolt distance. It is a 50 mm. So we need to consider here 0.05 as a Z. And the center line of the plate is the next axis. For that, total depth of the purple plate is 200 divided by 2 is 0.1 meter. And the next one, we need to define the bolt distance. So that is again 50 mm from the top edge. So that the 200 minus 50 mm will have 150 mm. So that means 0.15 meter. So we are entering here as next grid line. And again here is a red color edge plate is 25 mm after anchor bolt. So it is 0.175 is the next grid line for the red color top grid. And finally the purple color top grid line to be enter as 0.2, that is a whole depth of the purple line. Then apply. So with this we had created all the grid line. So after creating the grid line we need to develop the element. So for that click the fourth icon from the top in the right hand side. Select walls. So here we need to define the thickness of the wall. So here already 20, if it is not there we need to give that, and the color code also we need to select whatever required for us. And here the grade of steel we need to select S35, and if you want we can give some name also here. So 20 mm plate we are giving here, we can add it here. And again for a stiffener plate, you can see in the picture the stiffener plate, the green color we had given as a 10 mm, so that 10 mm also we can give here. We can add, and we can give some different color like blue, add. So now we need to create the first plate, which is a 20 mm thick plate. Select a 20 mm thick plate, which is a purple color plate we are going to create. So the purple color plate you can see on the screen, the picture, that is 200 mm depth. So we can type here 200 mm, and the plate orientation should be up. If you are selecting, if you are going to draw from bottom, we need to select up and select this beginning tab so that it will display as a green color. Now go to the main window and select the corner here and right side corner here, so that you can see that a plate is developed here. Now we need to create the lifting plate element. For that again click this wall. So here the height we need to given as 0.15 meter as shown in the picture in the right hand side. So here we are going to draw from top, so we need to select down and select here beginning point. Click this point which is a center line of purple color plate and move this cursor little bit away from that. So you can see here this grid line 6 and 3 of purple line are matching in a straight line. So select this. So you can see that a plate element is created. Next we need to create a stiffener plate. For that select floors, select here 10 mm and shell model type, select rectangle, pick the point P1. So we know that from that picture the stiffener plate is going to start from mid of the red color plate or the purple plate. So the green color plate is the stiffener plate here. So that to be extended to bolt distance 100 mm. So first point we are picked there, and second point is this, and the third point we need to select the grid number 3. You can see that blue color line, reference line, which is passing through the grid line 3. So there we need to pick the grid line. So now the stiffener plate, that is a green color plate also created. So now we can develop other side also similar like the same pattern. We have modeled all the plates element now. So next step is we need to create the nodal point for bolts. So for that we need to click here to show the node numbers. So before creating the node number, and we need to select the node icon from right hand side top. From the top it is the fifth icon. Before that we need to select this and separate it from the other plates. So select the purple color plate or fixing plate and go to this edit in a new window in the top just below the menu, main menu, editing new window. So here you can see only the fixing plate. So now click the nodes. Node number is 1, start from 1, and select the exact grid line for the node plate. You can also check these dimensions by measuring with the tool command. So it is 200 in horizontal and 100 in vertical. So now the node point for bolt is created. Now again we need to create the node point for lifting. So we can select this plate again, go to edit in new window. So in the plate itself we can add using the same procedure node, and this grid should be matched to the grid line number 2. Now we get created the fifth grid for lifting. Then we need to make a hole for bolt and the lifting point. Now we can hide the grid line which is not required furthermore. So go to display after clicking the right click on the main menu and click here structure and untick or deselect this structural axis, click apply. Now we need to create the holes for the bolt and the lifting hook area. Click the shape or object icon which is fourth from the top right and select this circle, select center radius, and here that XZ select because this plate is in the view of XZ. You can see in the icon here axis icon which is showing XZ. So we are going to create the hole in XZ plane. So select this, and the radius we know that it is 0.015. It is 15 mm is a radius and the diameter is a 30 mm. We are going to provide 24 mm hole, sorry 24 mm bolt. For that extra we are giving some 3 mm on both the side. If it is required even the smaller hole also we can give like 26, but for our demonstration purpose we are considering 30 mm hole. So it is radius is 15 mm, and parameters also we need to select here and give here discretization, and the discretization it's edge with 9 we can give, or even 10 also we can give, no problem. And now we need to select this node number 1 after picking this point B, and the radius we need to enter here as 0.015. Click apply. So you can able to see node here. Similarly for 2 also we need to create. So we need to pick here. So once after creating this discretized circle object, we need to make nodes in that. We need to add nodes in that, so that these nodes, after that we are going to create a rigid link, so that the stress will be distributed within the grid of this hole itself, and that will be developed a rigid link, and that link to be transferred to the node number 1 2 3 4, so that we can able to extract the support reaction or bold reactions. So let me see how it is work. So click the node icon here, and in order to make a difference, we are going to create this node number starting from 11, and we need to select these coordinates and pick one by one. So this is somewhat very time consuming task. Of course, we need to do like this. So we already created a 10 number of node, 10 number of discretization. So after, we need to check this the count as we created the 10 number of discretization part of this object. If the node first number is start from 11, then it should end with 20. So similar, like for second node, we can start with the 21 node number, 22, 23, 24. So likewise, we need to create until 30 for this node part 2. So that is created. So 10 number of discretization node we had created. Similar, like for 3 and 4 also we need to do the same. Now we had created the node secondary nodes for all the 4 main primary nodes. So now we need to create the rigid link. So this picture in the right side bottom is not required, as we had created the model. We can move this little bit away. Now go to geometry, click additional attributes, click rigid link. So in that rigid link, we need to create a new kind of pinned join, or we can connect as simply we can give the rigid, and here we need to transfer all the loads to the node number 1. So click add. Now we need to define, we know that the primary node is 1 for this hole, and the secondary node start from 11 to 20. Click apply, so that you can see on this the circle is marked with lines, and gray, some yellowish color is highlighted. It means all the rigid links are formed. Similar, like for second hole also we need to do like that. Here the secondary start from 21 to 30. Secondary nodes are start from there, whereas the primary is 2. Similar, like the third one, it is start with 31 to 40 hole also. So now we had created for all the 4 holes. So then we need to create for node 5, do and select radius. Zero 0.025. So parameter contour or opening and discretization with the 10 number of edges. So with this object is 9. Apply. So we had created the discretized object or circle. So from that we need to create the nodes as we seen for 1 to 4. So here it is start with the 51 to 60. So once after this, we need to create the rigid link as which we had created for other 4 nodes. So for that, click geometry, additional attributes, rigid link. So here simply in primary we need to type 5 and secondary 51 to 60. So now all the rigid links and hole marking, everything we had completed. Now the model is perfect. Then the next step is we need to apply the loads. For applying the loads, we need to select load types. So click loads in the main menu, click load types, then create a load type as det load. Let it be as it is. Click add and click the second load as a live load. So click add, close it. So and apply the load. There are two methods. One is load definitions by clicking load menu and click this load definitions. That is one way. And the easiest way we can go with the load table entry. So here click the loads in the main menu and click the load table icon so that we can able to see a tabular format. So let we minimize this and click here Windows to view both the model and load table window. Click title horizontal. So here the det load we can consider as the self height of the whole plate 1 to 4 whole structure in minus z direction. The factor we are considering as 1. And for live load criteria we can consider the nodal point, nodal force which we had calculated in our Excel sheet. So here is the load which is showing in this area just below the table. So this load we need to apply on the node number 5. So we are entering here 5 and in y direction this horizontal force 25 kilonewton to be applied and in the z direction that is upward direction it is 43.31. So we can also view this load by clicking display in the main window, model window and click left hand side loads, load values, load symbols, apply. So you can see here the load which we had applied. So for det load if you select, this is selecting the entire plate in blue color, red color line is surrounding all over the plate. So it means the self height is applied for entire plates. So now the live load also you can see here after selecting this. So we had applied the necessary loads. Then the next step is to analyze. Before analysis we need to create the combinations. So click loads. So combination also we can do by table. There are three methods of doing the combination. One is manual combination, automatic combinations and combinations table. So let me do with the combination table which will be a quicker method. So here we need to drop down, we need to enter here det load 1.5 det load plus 1.5 live load. So applicable load cases we need to enter here. So first case det load we are applying 1.5 and case 2 also it is 1.5. So this is a one case and another case we can apply 1.0. So this is serviceability load cases, load combinations. It is just one is the factor for all. So these are the two load combinations. We can save and close this load combination table. Go to loads, manual combinations. In that you can see these load combinations are added here. Suppose, yeah, we need to change this to ULS instead of SLS. So select this load, click change and change here as SLS, because this one dead load plus one live load is a serviceability load combination. So we need to change this and click OK. Then if you go and check for this load case 3, it is 1.5 in both live load and dead load. So similar like the load combinations which is required as per the standard or code, or as per the technical specification, we need to edit here. Suppose you need to change this load combination number, then go to loads, click load types. In that you might have seen this 3, 4. Suppose if you don't want the load combination series number to be as a primary load, then you need to select this load case so that the load case number can be displayed here. Instead of 3, you can select 11 and modify, click the modify button, then the load combination number will change accordingly. Similar like for load case number 4 also, we can do the same like this, 21 and modify. So now the loads and load combinations is applied. Next one is we need to run the analysis. So click here the calculations icon. There are some instability is created because we have not provided any support conditions. So for that we need to select the node number 1 to 4. Either we can select on the model itself, or else we need to select from the node numbers. So 1, 2, 3, 4 are highlighted in yellow. So click on the object, you can select support as pinned, click yes. Now if you run the analysis, so the analysis is perfect. Now you can see the entire model with applied loads and analysis. So now I think that load view is not required. We can hide that. And now go to results, maps. We need to check the stress values, click stresses. So you can see here it is in case as 21. So 21 is a serviceability load case. We need to check with ultimate load combination. So here the stress value is coming 33.97 megapascal. If it is in YY direction, it is 43.43 megapascal. XY, that is in principal axis, it is 25.93. So we can say that in all the cases, in all the directions, the stress value is within the limit. That means we already selected the grade of steel as S355, which is having the yield strength of 345. So if it is, if we are considering the maximum of 33.97, so 33.97 divided by 345 is only just 10%. So it means our plate is within the limit of yield strength. Hence we can call it as a safe. So this is what the lifting plate analysis. Then in the next video, the stage 2, we will be discussing about the connection bolt design for this plate. Thank you. Look description for more related videos. Subscribe to this channel for more updates. Thank you.